Good day, students. In this clip, we're going to be going over one example on implicit differentiation. We're going to be looking at an implicitly defined relation. And then as indicated here, we're going to find the slope, dy dx at any point x on the graph. We're going to find all points where there are vertical or horizontal tangents and the points where the slopes is undefined. And then we're going to verify results using analytic geometry. So the relation under consideration is 9x squared plus 4y squared plus 36x minus 8y plus 4 equals 0. Alright, we can suppose that this is implicitly defined since it's not solved explicitly in terms of y. Alright, so let's first find dy dx by differentiating this relation implicitly, this equation. So we're going to find d dx of the entire equation, 9x squared plus 4y squared plus 36x minus 8y plus 4 equals, and then we are going to differentiate 0, d dx of 0. Okay, so to preserve equality, whatever we do to the left side, we have to do exactly the same thing to the right side of the equation. Okay, so let's go ahead and differentiate the left side implicitly. So we apply the power rule here. On this term, we're going to have the derivative of x squared is 2x. So if we multiply that by 9, we'll have 18x. It's going to be 18x dx, so that cancels out. So we have 18x plus the derivative of y squared is 2y. If we multiply that by 4, we'll have 8y. So we have 8y, and then dy dx, and then derivative of 36. Derivative of x is just 1, right? So 1 times 36 is 36. Minus derivative of y is 1. 1 times 8 is 8, so we have 8, and then dy dx. Okay? And then this is a constant, d dx of 4 is simply 0. So plus 0 equals, derivative of this constant is also 0. Okay, so now we need to solve this equation for dy dx, and that will be the equation that tells us the slope at any point on the graph of the equation. Alright, so what we're going to do is move all the terms without dy dx to the other side of the equation. So that's going to be 18x and 36. Okay, and then on the left side we'll be left with 8y dy dx minus 8 dy dx equals negative 18x minus 36. If you subtract 18x and 36 from both sides, that's what you get. Alright, in order to be able to isolate dy dx, we need to factor out dy dx from these two terms. So we have dy dx times 8y minus 8 equals negative 18x minus 36. Now we're going to divide both sides by 8y minus 8 to isolate dy dx. So divide by 8y minus 8, and then divide by 8y minus 8. Alright? So that's going to give us, it's going to tell us that dy dx equals, now if you notice, I can factor out a 2 from the numerator and the denominator, right? I can divide the numerator and denominator by 2. But let me just factor out a 2 so you can see it clearly. If I factor out a 2 from the numerator, I'll be left with negative 9x minus 18. And then from the denominator, if I factor out a 2, I'll be left with 4y minus 4. Alright? And then I can divide the 2's out. 2 goes here 1. 2 goes here 1. So the slope at any point on the graph of the equation, the y dx, is given by negative 9x minus 18 divided by 4y minus 4. All right? So there goes the answer to part A. All right, let's shift our attention to the second part, part B, where we're going to find horizontal and vertical tangents. Let's start out by finding the points where we have vertical tangents. All right, so let's title it vertical tangents. All right, so what does a vertical line look like? A vertical line goes up and down, and we know that the slope of a vertical line is undefined. Okay, so if the slope of a vertical line is undefined, what will help us find the points where we have vertical tangents is where we're looking for points where dy dx is undefined. So anywhere that dy dx is undefined, we're going to have a vertical tangent at that point. So if we see that if this equation represents dy dx, what will make this expression undefined? It's when you divide by 0, right? So all we'll do is simply find where the denominator of this expression is equal to 0. So we'll set 4y minus 4 to 0, and the y value will tell us where the slope is undefined. Okay, so let's solve for y. We have 4y equals 4. Divide both sides by 4, we have y equals 1. So when y is 1, we have vertical tangents. Well, this problem wants us to find points. We've just found the y value, so let's go ahead and find the x value where we're going to generate vertical tangent lines. Okay, so what we're going to do is we're going to substitute this value into the original equation that we had at the beginning, and then we're going to solve for x. Okay, so we had this original equation, we're going to plug our y value here and then solve for x. Okay, all right, so let's go ahead and do that. We're going to have, let's see, we're going to have 9x squared plus 4 times 1 squared plus 36x minus 8 times 1 plus 4 equals 0. Okay, if we simplify this, we'll have a quadratic equation. So it's going to become 9x squared plus 4 plus 36x minus 8 plus 4 equals 0. All right, and then we'll have 9x squared plus 36x plus 4 is plus 8 minus 8 is 0, so equals 0. Okay, the constants cancel out. All right, so from this equation, I can factor out 9x, and I'm left with x plus 4 equals 0. So if I solve this, I'll have 9x equals 0, or x plus 4 equals 0. Okay, so if I divide both sides by 9 here, I'll have x equals 0. If I subtract 4 from x here, from both sides here, I'll have x equals negative 4. Okay, all right, so these are the x values of the points where I have vertical tangents. All right, so let's go ahead and write down our final result. Points of vertical tangency are, notice y is constant, okay? So y is the same, sorry. So 0, comma 1, and negative 4, comma 1. All right, so those are the 2 points where we have vertical tangents. So let's keep this in mind. All right, next we're going to be looking for points of horizontal tangency, okay? Points where the tangent lines to the curve of the equation are horizontal. Okay, so let's go ahead and write down the title of that section. This is the second part of part B. So you're looking for horizontal tangents. Horizontal tangents. All right, so what do we know about a horizontal tangent line? We know horizontal lines go left and right, right? So if a horizontal line goes left and right, parallel to the x-axis, what is the slope? The slope of a horizontal line is 0, right? So what will help us find the points on the curve where the horizontal line is a tangent? Well, what we'll do is simply set the derivative dy dx to 0. Okay, so any point where the y dx is equal to 0, that's where you have horizontal tangents, all right? So we know what the y dx is. We figured it out earlier. So the y dx in its reduced form was negative 9x minus 18 over 4y minus 4. So what we're going to do is simply set that to 0, okay? Now let's solve for let's solve this equation, all right? So if we cross multiply, we're going to end up with negative 9x minus 18 equals 0. So in essence, our focus is the numerator. And then if we add 18 to both sides, we'll have negative 9x equals 18. Divide both sides by negative 9. You end up with x equals negative 2. So that's the x-coordinate of the points where you have horizontal tangents. Okay? Now the next task is to find the y-coordinates of the points where you have horizontal tangents. In order to do this, we just simply plug in the value of negative 2 for x in the original equation. Okay, so if we do that, we plug it in, we have 9 times negative 2 squared plus 4 plus 4y squared. Let's try that again. Plus 4y squared plus 36 times negative 2 minus 8y plus 4. And that equals 0. All right, so if we simplify this equation, we're going to end up with a quadratic equation. So let's go ahead and simplify this. We'll have negative 2 squared 4 times 9 is 36. 36 plus 4 y squared minus 72 minus 8y plus 4 equals 0. Okay, so we can rewrite this in standard form. We'll have 4y squared minus 8y. And then if we combine 36 plus 4, 36 plus 4 is 40. Negative 72 plus 40 is negative 32. So minus 32 equals 0. All right, if you notice, 4 can go into all three terms, so we can divide by 4, and then we'll have y squared minus 2y minus 8 equals 0. Okay? Alright, so let's go ahead and factor this. I'm going to factor this using the AC method. So I'll make my little diamond. X right here. AC goes on top. AC is negative 8, and B is negative 2. So the two numbers are multiplied to give you negative 8 and add to give you 4 is a variation of 4 and 2. 4 is negative. Okay? Alright, so let's plug that in. We have y squared minus 4y plus 2y minus 8 equals 0. Break it down the center and factor by grouping. So from the first two, we can factor out a y. And then we have y minus 4. And then I can take out a 2 from the second two, and I'm left with y minus 4. And in the factored form is y minus 4 times y plus 2 equals 0. Okay, if we solve this 2, we have y equals, let me show you the intermediate steps. Use the zero product property. You set both factors to 0. y minus 4 equals 0, y plus 2 equals 0. And then you see that y is equal to 4, or y is equal to negative 2. Okay? So let's write down what this means. So what this tells us is that the points, the points of horizontal tangency, are, let's see, they are negative 2 and negative 2. And negative 2 comma 4. Okay, the x-axis coordinate stays the same, but the y, we have two y coordinate values. Alright, so there you have it. Now we're going to shift attention to part C, where we're going to verify the accuracy of our results using the tools from analytic geometry. All right, so let's title this verification. Verification. Verification using analytic geometry. Analytic geometry. All right, so let's consider the equation that we had earlier and see if we can determine what kind of graph that is in geometry. So we have 9x squared plus 4y squared plus 36x minus 8y plus 4 equals 0. Now, if you take a look at this equation, you notice that you have two squares, which makes it an ellipse, circle, or hyperbola. And if you inspect the other variables, you do not have any products of x and y. If you have a products of x and y, that complicates things a little bit. So you don't have any products of x and y as any term. Every other first degree variable stands alone. Now, since you have a plus between the squares, that tells you that this is a circle or an ellipse, but since the coefficients of the squares are different, that tells you that this is going to be an ellipse, okay? All right, so let's go ahead and we're going to place this ellipse in standard form and graph it, and then we're going to show how it connects with the results we got earlier. All right, so we're going to complete the square here, but before we do that, we're going to organize our variables, put the x's together, 9x squared plus 36x, and then the y's together, 4y squared minus 8y, and then subtract 4 from both sides equals -4. Now, we're going to isolate the squares first so that we can complete the square. So we factor out 9 from the x's. Well, let me partition it into the two respective worlds so we don't get confused. So focusing on the x's, I can take out a 9 so that this x squared stands isolated. 9x is going to be x squared plus 4x. And then I can factor out a 4 from the y's, and I'm left with y squared minus 2i. Okay, now we have two incomplete squares, so we're going to complete the square. So to complete the square, you basically add b over 2 squared to both sides. Okay, so we're going to have 9 times x squared plus 4x. I'm going to add b over 2 squared here to complete the square in the x world, and then plus 4 y squared minus 2y, and I'm going to add another term here, b over 2 squared in the y world to complete the square. And then on the left side, I'll have -4. On the right side, I'll have -4 plus 9 times that number I introduced here. I'll multiply 9 by that number, and then plus 4 times the number I introduced in the y world. Okay. All right, so to find those two numbers, I'll just do b over 2 squared. You can do that mentally, but let me show you what they are. So for the x, b for the x is 4. So I divide that by 2 and square it, which is 4. Okay, so if I put a 4 here, that makes this a perfect square. So I put a 4 here also. 9 times 4 is what you put on the right side. And then for the y world, b is -2. If you divide that by 2, you get 1. If you square it, you get 1. So I can put a 1 here, and then put the 1 here to preserve equality. Okay, so we want to factor difference of squares. It's pretty easy. Just read the first and the last term, and then bring down the middle sign. So the factored form is going to be 9 times x plus 2 quantity squared plus 4, same story with the y world. You square root the first and the last term, and then bring down the middle sign. So it's going to be 4 times y minus 1 quantity squared. And then here we have -4 plus 36 minus 4. The 4's cancel out, so you're left with 36. Now, to put this in standard form for ellipses, we just have to set it equal to 1. So what we'll do is divide everything by 36. Divide by 36. And divide that by 36. Okay? So that's going to give us the equation x plus 2 squared. Now this 9 goes into 36 4 times. Okay, plus 4 goes in at 36 9 times, so we have y minus 1 squared over 9 equals 1. All right. Okay, so my properties of my ellipse, I'm not going to tell you all the properties, just a few of them that are sufficient for me to generate the graph. I just need the center and the direction of the major and minor axis, okay? So the center, you take the opposite of the number next to the x, -2, opposite of the number next to the y, +1. And then for your axis, you take the square root of the denominators, all right? So the square root of 4 is 2. And since it's under the x-axis, which goes side to side, that means you're going to go 2 units side to side. That's the length of your semi-minor axis, all right? And then you root 9, which is 3, and that was under the y-axis. And since it's bigger, it's going to be the length of your semi-minor axis. Semi-major axis. Okay, so this is enough information to generate the graph of the relation, which is an ellipse, as we discussed earlier. So you draw that's my y-axis, and there goes my x-axis. So I'd like to draw the center first. The center is at -2, 1. So 1, 2, 1, -2, 1, there goes your center. Okay, so following the direction of our axis, 3 units up and down, 1, 2, 3, to give you the vertices of the major axis, okay, the major vertex. So there goes one major vertex, the second major vertex. To draw your minor vertices, you're going to go 2 units side to side from the center. Okay, so 1, 2, 1, 2. All right, so let's go ahead and draw our ellipse. All right, so there you have it. Okay, so where are the vertical and horizontal tangents? It's very easy to see where they are, right? So let's go ahead and draw the horizontal tangents first and label them. Horizontal tangents go to the first one. It's the first one right here. First horizontal tangent, and this is the second horizontal tangent. Let's write out what the coordinates of those points are and see if they agree with our initial results that we use using the tool of calculus. So this is the first horizontal tangent. Coordinates of this point, is, what is it? Let's see. So we just count. So you go 1, 2, -2, 1, 2, 3, 4. So this is -2, 4. And we can see that this agrees with the first answer we got. And then this one is 1, 2, -2, 1, 2, -2. So this is -2, -2. Excellent. That's exactly what we got. All right. So this is a horizontal tangent. And what do we know about it? Horizontal tangent dy dx is equal to 0. Okay, so let me use a green line to indicate where they are. So this is the first horizontal tangent, and this is the second horizontal tangent that we have. All right. Okay, how about our vertical tangents? So where are the points where we have vertical lines that are tangent to the graph of this equation? We can see that we have one right here. Let's go ahead and graph that. So just make it a little red so you can see it. So there's the first vertical tangent, and this is the second vertical tangent. Okay, so let's find the coordinates of those points and see if they agree with the answers that we got initially. Let me shift that to the right a little bit. Oopsie. All right. So this is the first one right here. What are the coordinates of this point? Coordinates of this point are 1, 2, 3, 4, -4, and 1. -4 and 1. And then this is this is the other point of vertical tangency. Let's just put an arrow over here, and the coordinates of that point are, let's see, simply 0 and 1. Okay, so we see that this agrees perfectly with what we found out earlier. So these 2 points, what are they? These are your vertical tangents. Write it down. Vertical tangents. Okay, and we remember that dy dx is undefined at these 2 points. Okay, that's when you have vertical points of tangency. Okay, so there you have it. So thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel. Please post a comment to let me know what you think. Click like if you liked it. And do feel free to share it with your friends with your social networking program. More clues can find on mathgrowserve.com/calculus. Thanks again for watching and have a wonderful day.